Hello everyone! Today I will introduce you to the DeepHyper software for the ALCF Computational Performance Workshop of May 2020. The team is composed by project leader Prasanna Balaprakash, computer scientist at Argonne, myself, Romain Egele, and AI master students working on this project since June 2018, as well as some members of the data science group and MCS division at Argonne, and external contributors. Let us start with the way of deep neural networks. The typical way of building neural networks is by a long trial error process. We first evaluate on our training data, then, depending on the performance, we're going to evaluate our model on a testing dataset, and with iterations, we are going to collect more data and increase the model complexity. Once we are satisfied with the performance, we keep our model and use it online. This process can introduce many biases in the selection of a model if a careful methodology is not followed. It is also very time-consuming. I'm gonna use TensorFlow Playground to demonstrate a very inconvenient aspect of neural networks. The theory states that a neural network can approximate any function. Here, you can see on the right side of the slides a dataset of orange and blue dots that are the data that we want to learn. The background represents the learning of the neural network. On this example, we can see that the neural network is not able to learn the data well even after more than thousands of epochs. If we just applied slight changes to the neural network, by decreasing by one neuron in one layer and increasing by one neuron in another layer, we can see a much better performance. If we now want to increase the complexity of our model by adding more trainable parameters, for example in the last layer, we can add 2 neurons. And by adding 2 neurons, the network is not able to learn the data. Therefore, we made DeepHyper a scalable automated machine learning package for developing deep neural networks. It is available on GitHub. It has a free accessible online documentation. What is automatic machine learning? Automatic machine learning is the way of finding automatically a learning algorithm. It encompasses hyperparameter search and neural architecture search. Hyperparameter search can be applied to any kind of algorithm. It is to optimize real parameters, discrete parameters, or categorical ones. However, neural architecture search can be applied only to the field of deep neural networks, and it is applied in particular on discrete search space. DeepHyper encompasses 3 main features: the hyperparameter search with IMBS algorithm, for example, the neural architecture search with reinforcement learning, genetic algorithm, and random search, and a set of workflows to be able to run these searches on your local laptop, on a cluster of machines, or on a supercomputer. What is the DeepHyper workflow? You will always start with a dataset coming from the industry or researcher. Then you will have the problem setup at the first step. This is where you're gonna define if you want to do regression or classification. This is where you're gonna define which data do you want to predict, which data are you going to use to build this prediction. After this step, you're gonna choose or define metrics to select the models. This step defines how you're gonna rank the quality of one model, and it is of particular importance. If we take the cancer example, where we want to help doctors diagnose people with cancer, we do not want to miss sick people. Unbalanced datasets have to be looked carefully as well. Hence, using always the same metric, such as accuracy, is not often a good idea. After this second step, you're gonna launch an automatic search. Using the outcome of this search, you're gonna rank a set of best candidates and select some to retrain. Then, you're gonna have a final model that's gonna be able to use. Let's go into much more detail. The problem setup. If you have your datasets which contain 100% of your data, you're gonna split it in 3 parts. The training part, the validation part, and the testing part. The testing has to be kept for the evaluation of the final model you have. The training is used by the software to train each neural network. Then the validation set is used to evaluate their performance in our search algorithms. The load data function you're gonna define in DeepHyper is then gonna return the training data and the validation data. We let the user for now handle the prediction and evaluation of the final performance of its model on the testing dataset. The problem definition is gonna contain a random seed for reproducibility purpose of your research, and then you're gonna add hyperparameters such as alpha, which here is a parameter in the range 0, 1, and it's a real hyperparameter. You're also gonna define starting points. Here, alpha equals 0.01. Starting points are of particular importance to advise the search at the beginning and help it search at the right location. If you have an already good starting point, it's important to give it to the search. Then, the definition of metric for model selection. On this slide, you can see a classical run function. The run function is used by the software to evaluate your current model and return an objective we want to maximize. In these run functions, you have to fix a random seed, again for reproducibility purpose of your research. Then you're gonna load the data, or it's gonna be handled sometimes by the software. You're gonna create your model given a current configuration, where the configuration is actually a dictionary containing keys corresponding to the hyperparameters defined in the problem. You're gonna fit your data with the training set. You're gonna evaluate the model with the validation set and a metric. You're gonna compute any transformation of this score and return it. Okay, automatic search are nice, but how to choose the search I want? Or which search will be good for my problem? The hyperparameter search is good to use if you already have a good baseline model. For example, a scikit-learn based model, a neural network, and you want to tweak some of its parameters. The automatic machine learning for scikit-learn can be used if you don't have any good guess at the beginning and you want to explore many different kinds of classifiers, such as random forest, extreme boosting. Neural architecture search, NAS, if you do not have a reasonable NN model, it's good advice to use it. You also have to be careful that your current neural network or the idea of neural network you would like to use is compatible with the software because of the various topology of neural networks available today. Once you choose your search, how to scale or run your search? The first question you have to ask yourself is how long the baseline model runs. If it's less than 2 minutes, then it's awesome. You're gonna be able to run the search on your single machine such as your personal laptop, and it's gonna take 1-2 hours to have a good result. If the search is between 2-20 minutes, then you're gonna be able to use Theta, Cooley, or any cluster of machine. You're gonna be able to access the IMBS search, regularized evolution, PPO, or random. For the IMBS, the limitation of number of nodes is 256 nodes in parallel. Afterward, the master node becomes a bottleneck and it's not efficient to use more nodes. It doesn't help you to find a better result, and the node utilization is really poor. So you're gonna lose hours of computations for nothing. For the regularized evolution, RegEvo, from 512 nodes, the node utilization starts to drop. Larger the node count, bigger the population size should be. For PPO, the limit on Theta is of 1000 nodes. If you increase the number of nodes from 256 to 1000, you have to be careful and take into consideration the number of agents you're gonna launch in parallel. It is defined by the number of nodes used by the master job. The random search, it's random. The master node is not really a bottleneck for now, and you can launch it with a lot of nodes, but it's not a good idea. If your model is taking more than 20 minutes to run, for example, if you have a big dataset or big neural networks running for thousands of epochs, it is good to reduce the size of a dataset and to reduce the number of epochs to be able to discriminate the model learning better than others. Thus, you can find a way to simplify your current problem just to be able to run the search and select the good models. Afterward, you're gonna be able to run it at scale on the Theta or on your local machine. If you don't do this, using this search with model taking too much time to run will not be efficient, because the search will not be able to iterate enough and find something meaningful for your problem. After these steps, we're gonna select the best set of candidates. To do so, you can use the DeepHyper analytics command line, which help you to analyze the result and to rank them. From this outcome, you can first verify that they are meaningful, rank them, select a top K of models, and then launch a post-training procedure for neural networks in particular, with a greater number of epochs this time. These procedures can be launched in parallel. This means if you selected 50 models, you can train them in parallel on Theta for thousands of epochs, for example. Then you have your final model. You should not have used the testing set till now. Evaluate the best model you have on this dataset, the testing dataset, and you will have its final performance. What are the good practices with DeepHyper? The den of DeepHyper. It is really important to follow good practices. With such a software, you can consume a lot of hours on a supercomputer without interesting outcomes. Always start with a baseline to identify your problem. This is why in DeepHyper we provide a sub-package with classification baseline or regression baseline. Then, always try it on your local machine before running experiment at scale, and when it's possible, you can run it only on your local machine. Always try it in a debug queue before running experiment at scale, and always check that the results are meaningful and make sense for your current problem. Now we're gonna go through three parts: the general hyperparameter search, the hyperparameter search for automatic machine learning with scikit-learn, and the neural architecture search. Let us start with the general HPS. The hyperparameter search is defined in a B-level optimization framework. The lower level problems is applied on the training data. We want to minimize the error of a model on training data, and thus we optimize the weight W. The upper level problem is applied on the validation data, and we want to minimize the error, but this time playing on the architecture space and the hyperparameter space. AMBS, or asynchronous model-based search, is a Bayesian optimization method. It relies on the LCB acquisition function and tries to sample efficiently points in the search space. In DeepHyper, to make it asynchronous, we relied on a layer strategy, which helps you make a good compromise by tweaking the parameters of the search between exploration and exploitation. How does a problem definition look like in DeepHyper? You're gonna import a problem such as an hyperparameter problem, HP problem, and you're gonna define a set of dimensions such as epochs here, which is a value of integers between 5 and 500. Activation L1, which is a categorical hyperparameter taking 4 possible values, and a dropout learning rate, dropout L1, which takes a value of real between 0 and 1. Now, let's move to the hyperparameter search for automatic machine learning with scikit-learn, for example. In DeepHyper, we provide you a wrapper function that you can use in your run function, and that's gonna look over different classifiers of scikit-learns. Thus, to use it simply, you just have to define a load data function, returning this time the combination of the training and validation set as only one array, x, y. The split is gonna happen in the run function of AutoScaler1, and it's gonna search over different classifiers and hyperparameters of each of these classifiers. If you want to do and build your own settings for an automatic sklearn kind of search, you can do it like this. You will define a problem using the config space package. Here we, for example, define a classifier, which is a value that can take different value of classifier. Then we define n estimators, which is hyperparameters that can be applied to 2 of our classifiers, and we put a condition on this hyperparameter. Thus, we can put constraints on our search space. After, for the model evaluation in the run function, you can do something like this. If your model is not taking too much time to be trained, you can use a k-fold settings to reduce the chance of having a lucky findings. Then, if you have unbalanced data set, the smooth algorithm can be used to oversample your data and make a balanced training data set. The njobs parameter can often be used in scikit-learn or other plugins, packages, and it helps you to distribute the computation on the CPU. How to visualize your results? I advise you to use Visual Studio Code on your local laptop, plus, for example, Rainbow CSV plugin. Thus, you can quickly explore the results file, which is a CSV, with colors. Then, by using the Sentence plugin on Visual Studio Code, you can have quick visualizations. For example, here we take the time according to the objective. And we can quickly see that AdaBoost classifiers are performing better than others, and directly see what n estimator parameter was used for this AdaBoost performance. You can also do another kind of visualization by using the stacks. Here we sorted it by objective and the colors show the objective. Thus, you can see that the search is sampling a lot more ADABUS and they are generally performing better than other classifiers. Now, let's move to neural architecture search. A discrete space embedded as a directed graph where each node represents a choice between different operations. That's what is the neural architecture search space. Okay, so for each node, we have a possible set of operations. Now, let's see how it works. At the beginning, each evaluation of the search will start with the graph being emptied. Then it's gonna take a sequence of decisions. Here, for example, it made decision 1 corresponding to dense 10 ReLU. Then decision 0, it's creating a connection with the previous layer and with the input layer. And then you continue. And it's building a possible neural network corresponding to the decision summary on the left side. Thus, we can have an algorithm creating models corresponding to neural networks here with different topologies. And we load this model, we'll apply an automatic feature engineering and preprocessing. We'll train this model and use the feedback to help the search learn and generate better models. We have two main algorithms in the plugin, the reinforcement learning. When you start with a common base on knowledge, then you're gonna launch agents in parallel. Each of the agents is gonna work with a batch of architecture that they are gonna sample asynchronously or synchronously, depending on the settings. And they're gonna have feedbacks. Then gonna propagate this feedback and they're gonna learn together. The other search is the aging evolution or regularized evolution. In these settings, we sample a set of architecture. We select a subsample of this population. We run these samples and select the best one. We apply a mutation on it, which creates a new models. We evaluate the model, and once it's evaluated, we put it back to the population. By adding a new individual to the population, our population now exceeds the capacity, and we kill the oldest neural networks created in the population. And we iterate. Those algorithms, in particular the PPO algorithm, have been tried and explained in a paper on the cancer distributed learning environment. We use 3 different problems, the combo, UNO, and NT3 problem. I'm gonna show you some results about these 3 problems. In this plot, you can see the learning of an asynchronous PPO, a synchronous PPO, and a random search. We can see that the asynchronous is often learning faster than the synchronous one, but they end up with a similar result. And the random search is always below this search's result. If we take UNO in particular, when we are using 3 inputs, the cell RNA sequence, the drug dose, the drug descriptors, and the drug fingerprints. In these settings, we want to predict the tumor dose response across multiple data sources. We're going to try to optimize this architecture with our algorithm. And here are the results. The black triangle is the baseline we started with. Then the automatic search sample all other triangles, and you can see that we are likely to improve the prediction performance corresponding to R-square. We reduce the number of parameters, which help us to do prediction faster and training faster. And also, the time of training is better. In this plot, the higher is always better. Let's see the summary for the 3 problems. We can see that on the combo and NT3 dataset, the performance has not been improved from far. But at least we are finding models performing as well as the baseline, and which is really good. Also, the number of parameters is often much lower, Thus, we can have neural networks training much faster and help researchers iterate faster in their research. For the who know problem, we have a model performing much better. If we summarize the result of this search, applied on one of these problems, we had a quite big number of possibilities. We explored a very small part of the search space as expected, which totalized a number of 18,000 unique models found, using 256 nodes during 6 hours. And we've selected the top 50 best models. This project has been developed with the support of the Department of Energy and Argonne National Laboratory. Thank you for listening to this talk, and if you need more information, please feel free to contact us or read the online documentation. Have a great day.